Now, up to this point, we've talked primarily about what we can call translational motion. So here we have a ruler or something, and in this picture, it's just moving translationally or linearly. And so the object as a whole moves along a trajectory, but it does not rotate. We've talked about rotational motion a little bit, but objects, of course, are allowed to rotate. And we haven't dealt too much with this, and so we're starting to now. And then what we can have is the combination of both of those. And so here it's a ruler that's moving along some parabolic trajectory, but it's also rotating. We want to be able to account for both these types of motion. A really important concept will be the axis of rotation, which is the line things rotate about. And basically everything we talked about would be in definition to the axis of rotation. So here's, it's sort of a simple idea, but it can be tricky in practice, and so I just want to go over it. So here's a gray disk rotating, and this yellow dotted line is the axis of rotation. We can view it here, where it's basically head on. The disk looks really skinny, and this looks like a little line, a yellow dotted line. We can also look at sort of a bird's eye view here, where the axis is just a little dot. Okay, so you got to be careful, but all of our definitions will deal with the axis of rotation. Now, when dealing with a rotating object, our old-fashioned variables come up short, and our old-fashioned variables would be position, velocity, linear velocity, and linear acceleration. And why do they come up short? Well, suppose we have these 5 blue dots, and this little green disk here is rotating about its axis of rotation. When we do this, all right, all these dots are going to go a different distance, right? This inner one goes a much shorter distance than the one that's a little bit further out, and they're all going to have different speeds and accelerations, linear speeds and accelerations. So our old-fashioned values are going to be different for all 5 of these points. And so what we did is we created a new angular rotational value, okay? And basically what that means is all these points are going to go through the same angle, the same amount of radians in the same amount of time. They're going to do the same number of revolutions in the same amount of time. And so we define the angular displacement, all right, which is usually measured in radians. And basically, you know, if I was to draw these points again, so 2 points here and here, as we travel here, they travel different linear distances, but they'll travel the same amount of radians, the same angular distance. And real careful here that it's always positive if counterclockwise and negative if clockwise is our definition. And the whole point is that all points have the same angular displacement. And further, we defined the angular velocity, which is the analog to the linear velocity, and the angular acceleration, which is the analog to the linear acceleration. They all have units that now, instead of involving meters, involve radians. And the really important point is that all points on some rotating rigid body is just a really fancy way of just saying an object that its shape cannot change, are going to have the same angular velocity and the same angular acceleration. That's why we're going through all this business, is to make our lives easier, even though at first it may seem like it's making things more complicated. And what we did with this then, so again, we're going to find that for basically everything we've dealt with before in physics, so here x, v, and a, we now have a rotational analog, and we're going to find that this is going to continue. And we did this a couple of weeks back, where we took the linear equations of kinematics and put them into rotational form. So they have the same shape as the equations we've been using. They look like they're in kind of like a different language now. So real quick, just a little refresher here. And so here we have a fan blade that's rotating in the clockwise direction. We want to know is what are the signs of omega and alpha, and assume the fan blade is speeding up. What do you think? All right, hopefully you got that they're both negative. So clockwise is the negative direction, and so since it's rotating clockwise, then this will be negative. And it says that it's speeding up, which means the acceleration will be in the same direction as the angular velocity, and so that'll be negative as well.